Okay, so I hope you enjoyed the quiz. So it was actually without any mathematical derivations, just to give you some questions to check yourself about the understanding of the concepts. So let's go quickly through the questions. You can see first question. Using the MVDR filter, we can obtain a higher noise reduction factor when, which one is true? It's correct? I didn't hear. A, B, C, D. A, okay, good. Because when Rx, the rank of Rx is smaller, so the noise subspace is larger, so we can reduce more noise and we get higher noise reduction. Good. To increase the output SNR, we need A, B, C, D. Okay, let's check it. C, to increase the output SNR. So if we decrease L, the output SNR will be higher or lower? What is the effect of L on the output SNR? So which one do you think is correct? You said C? D? D. Okay, D. If we increase L, we use more information because we use the correlation between any two samples. When we increase L, we can use more information. That means the correlation between distant samples. That's why we can increase the output SNR. Actually, when we increase L, what happens to the mean squared error? Decrease. So both the SNR, output SNR increases and the MSC decreases. Okay, let's move on. The desired signal distortion index that is obtained with the MVDR filter, A, B, C, D. D, smaller than the noise reduction factor. That's true, because the desired signal distortion index actually is 0 for the MVDR. So it's smaller than the noise reduction necessarily. The noise reduction is positive number. Okay, the gain in SNR, A, B, C, D. Which one, C or D? Or C, okay. The ratio, let's read it. The ratio between the noise reduction factor and the desired signal reduction factor. Okay, but even if you don't remember, think about, okay, so maybe you remember it's some ratio, but you're not sure if it's C or D. Okay, let's think about it. And the noise reduction factor. When you increase the noise reduction factor, it means that you suppress more noise, right? So what happens to the gain in SNR? Increases. Exactly. So it should be in the numerator. Okay, so it's the ratio between the noise reduction factor and desired signal reduction factor. Okay, let's move on. 5. Low SPCC between V and Y indicates A, B, C, D. B, let's think about it. Okay. So the squared person correlation coefficient, if it's low between V and Y, what does it mean? If it's low, it means that the noise is low. Okay? If the noise is low, it means that the input SNR is high. So it's B, high input SNR. Okay? 6, to increase the noise reduction factor, which filter do we need to choose? Which one? B. Okay, so B, trade-off filter with mu larger than 1. Is it correct? What about maximum SNR filter? So the maximum SNR filter actually achieves the maximum noise reduction. Okay? So maybe it's confusing, which is true that we can use the trade-off, but the maximum SNR, it can increase as much as possible because it increases the output SNR, which is achieved by maximizing the noise reduction factor. Okay? 7. So even if you made mistakes, it's fine, you know, it's just to practice the terms and so on. High SPCC between X filter desired and Z indicates A, B, C, D. What? C. Let's think about it, of course. So if we, when we talk about correlation between X filter desired and Z, it relates to the output SNR. So we can remove B and D, okay? And if it's high, it means that the output SNR is high, right? So it's A, okay? Because if these correlate, high correlation, it means that the output SNR is high. So it's A. The next one, 8. Using the Wiener filter, when the input SNR increases, A, B, C, D. What do you think? B? Okay. Which one? Last one, D. Okay, let's see. Okay, so with using the Wiener filter, the input SNR increases. So the noise reduction factor decreases. And the desired signal reduction factor decreases. So both decrease. Okay, so if the input SNR increases, it means that we have less noise in the input. So if we have less noise at the input, the Wiener filter doesn't need to work much. So it's less aggressive. So it reduces less noise, which means that the noise reduction factor decreases. Okay, good. What about the desired signal reduction factor? Also decreases because we have less distortion because the input SNR is high. So it's D, correct. 9. The MVDR filter can be derived by A, B, C, D. Okay, let's check C. Okay, so the MVDR with C, it's minimization of JNH subject to this. Okay, so we can remove A and B because the MVDR is distortionless. So it doesn't minimize JD. It minimizes JN, the variance of the noise, or the MSC that is related to the noise. So it's either C or D, according to this, the beginning. It minimizes JN. Now, regarding the constraint subject to, so this is the signal subspace. So this is the distortionless constraint. So C, correct. Okay? Number 10. To find the maximum SNR filter, we need to compute A, B, C, D, D. Okay, the D, the maximum eigenvalue of RV minus 1 Rx. Okay, correct. Okay, so a simple quiz. I hope you enjoyed. Okay, now I'll show a short video. This one. It's from the IEEE Signal Processing Society. hope it works. Okay.
Have you ever wondered, how do Amazon Echo and Google Home understand my questions? The answer is signal processing, the science behind our digital lives. Computers and smartphones have allowed speech recognition for quite a while, but deploying that technology in home assistants has been much trickier. With smartphones, commands are often spoken very close to the microphone, whereas with home assistants, commands are often spoken anywhere within a large room, which is much farther from the microphone. This means the device must process not only speech, but also echoes and conflicting noise that deteriorate accuracy, including the TV, kitchen appliances, and other people talking. Utilizing a trigger
Somehow was removed. Maybe the light to dim the light, or maybe if it's okay, it's okay. But is it okay? Okay. Is it visible? No problem? Okay. Sorry, it went out.
Often spoken very close to the microphone, whereas with home assistants, commands are often spoken anywhere within a large room, which is much farther from the microphone. This means the device must process not only speech, but also echoes and conflicting noise that deteriorate accuracy, including the TV, kitchen appliances, and other people talking. Utilizing a trigger word like OK Google or Alexa activates the home assistant to recognize a command or question. Once the device is active, it sends all following speech and sound streams to data servers that process the request. The wide variety of conflicting noise results in extremely complex sound waves, making it more difficult for the home assistant to understand, process, and respond to commands embedded within. For devices like Amazon Echo and Google Home to successfully analyze complex speech waves and determine the embedded command, they use far-field speech recognition, whereby signal processing engineers conduct specific machine learning techniques. Far-field speech recognition can be enhanced in two ways. The first is multi-channel speech processing, which uses multiple microphones to allow signals to be enhanced from some directions and suppressed from others. Next time you use your Amazon Echo, notice that it purposefully lights up in the direction in which you're speaking. The second is multi-condition training, which trains the device to find the command within all the sound waveforms, including the speaker's reverberation, others talking, as well as TV and kitchen appliance noise. This statistical model is trained from a myriad of examples. To ensure accuracy, signal processing engineers create countless situations where sound waves are emitted and picked up by microphones in different areas of the room. Google, for example, uses a room simulator to generate such signals from various rooms that are small, big, noisy, echo-prone, and more. Combining multi-channel speech recognition and multi-condition training to achieve far-field speech recognition allows signal processing to decipher complex speech waves and fuel this new wave of home assistant technologies. We owe much of that success to advancements in signal processing and machine learning in just the past decade. Will you be part of the next wave of signal processing fueled technology? Visit us online to learn more.
Okay, so I just also want to mention that this year the main conference of signal processing ICASP, it's going to be in Hyderabad in April. So it's very close and first time in India. So I hope you will have the opportunity to attend this conference, to see some demos, some lectures on different kinds of signal processing, array processing, and so on. Okay. Okay, before we continue, do you have any questions about the material we've gone so far? Okay. So today we will continue with single channel signal enhancement, but instead of the time domain, in the frequency domain. And yesterday we talked about motivation, why we need to work in the frequency domain, what are the advantages. So there are advantages to work in the time domain. There are also advantages to work in the frequency domain. Depends on computational complexity, the length of the filter, and actually the problem in the environment. So similarly to the time domain, single channel signal enhancement, we will describe the signal model, problem formulation. We'll talk about noise reduction with gains. We mentioned yesterday that it's possible to do noise reduction even with vectors that take into account the correlation between frequency beams. But we will neglect that to make things simpler. Of course, you can extend it. But then, the more information that you use, you need to estimate or to obtain this information reliably, which is not a simple task. Okay? We will talk about performance measures, similarly to the time domain. And then when we have performance measures or criteria, we can derive optimal gains. Lastly, we will, you know, that we don't work in the frequency domain, we work with windows. So we will extend it to implementation with the short time Fourier transform domain. And then you will also get assignment today, and you will have also an opportunity to practice with speech enhancement. So you will be able to record your own voice, to add noise, to hear it, how it sounds, and then to do speech enhancement, which means to reduce the noise and to verify what is the trade-off between noise reduction and signal distortion. Okay? But I don't want to give you too much homework. It's up to you. Okay? So I'll give you an assignment, and the other one will be an extension with a short-time Fourier transform. Whoever wants to do something beyond the assignment, I will describe what you can do, and then you can also practice this like a real problem. You know, it's fun, for the fun. Whoever wants to extend and has some time. Okay, so I hope all of you that submitted the first assignment, if you had any problem or question regarding that, please ask today. Maybe after we come to the second assignment, and if you have questions, we can talk about it, okay? Because it's important that you practice. I hope that with the MATLAB code, you didn't just take it as is and change parameters, but also to read how it looks like. It's also, you can keep all the MATLAB codes from the book. I also sent some chapters that related to this material. And it's useful, actually. Suppose that you want to do use this MATLAB code for other problems. So it will give you the basics, how to implement things that we learned in class based on the mathematics, how to implement it using a MATLAB code. It's very important. And then you will be able to write your own code. Things which are more sophisticated, okay? Especially when we will talk about the implementation in the short-time Fourier transform. Okay, we will talk about details which are important, and they are implemented in the MATLAB code, and how to do that. So I really encourage you to also to practice and read the MATLAB code and understand it also in this part, which when we reach that. Okay? even if you don't have time during this period of time, this week, you can do it afterwards. But it's important. Okay. So we start in the time domain. This is the model, just like we had in the time domain, but instead of working in the time domain, we transform the signals to the frequency domain, and then we have this problem. Y equals to XF VF. And as we said, that we want to simplify the filtering as much as possible, which means that we want to estimate X from Y alone. This is interesting, okay? So we have YF equals to XF plus VF, and we want to estimate XF using Y from the measurement YF. So you remember that when we talked about the time domain filtering, we said it's very difficult to estimate a single sample from a single noisy sample because we don't know how to separate it. And here we actually use a single frequency estimation of the clean signal from a single frequency noisy measurement. Okay, so what kind of information can we, do we need? How to do that? Is it possible to do that? Maybe we require information that is not available. So we have these questions. So you see, we work here in a more simple way to estimate the desired signal. And we need to know if it's possible or not. Okay? We need to think about it. What kind of information? Can we obtain this information from noisy measurements? Okay, so ask questions. Okay. Once we have this, we can do the inverse Fourier transform and go back to the estimate of the signal in the time domain. So we work, when we go further, we will move those. But for now, we assume we work in the Fourier transform domain, and we work with stationary signals. Okay, so we don't need windowing, and the length of the Fourier transform can be as large as we want because the signals are stationary. Okay, so we can define the variance of the measurement, the noisy measurement in each frequency. So actually, if we work on each frequency independently, we can actually remove the dependence on F, okay? Because we work on each frequency independently. So sometimes we keep the function of F, and sometimes maybe we can just drop it because we understand we work on each frequency independently. So here, YF is a scalar, right? So it's a complex scalar. And the variance of this complex number is defined like this. So this is its variance. And we can write it as the summation of two variances, variance of X and variance of V. So you see, when we work on scalars, everything is much more simple. Let's continue. If we do noise reduction with gains, it means that we need to find filter in the Fourier transform domain. So we multiply each noisy coefficient with a certain generally complex number. And then we achieve the enhanced signal. So you see, if we multiply with a certain H, for each frequency, it's different, okay? Different gain. That's why we call it gain, because it's not even a filter. It's just to a filter in the time domain, it's also a gain in the Fourier transform domain, okay? So we can just multiply it with different gains, and then we get two components in the estimation. One is filter desired, H multiplied with F, and the other one is the residual noise. So on one hand, we want that X filter desired will be equal to X, which means that the gain H should be 1. Ideally, we want to have this H multiplied with X to be equal to X for any X, for any desired signal. So ideally, we want HF to be 1 to reduce distortion. On the other hand, we want the residual noise to be as small as possible, low. So we want H to be close to 0 to suppress more noise. So the value of H depends on the performance measures. What do we want to achieve? And we can understand that if the input SNR is very high, probably we would like H to go as high as possible, closer to 1. Okay? So we can think of even like this. Makes sense that even that H can be a complex number, right? It can be a complex number because we work in the Fourier transform domain. It makes sense that H from here, it will be between 0 and 1. Even a real number, it can do a good job. I don't say that we restrict that and we are looking only for a real number, but I say that it makes sense that if we want to reduce noise, maybe it's between 0 and 1. So for each frequency, suppose that we know for each frequency the signal to noise ratio. Then if the signal to noise ratio for each frequency is high, then we will multiply it with a gain that is closer to 1. If the input SNR in that frequency is low, we will multiply it with H that is close to 0. Okay, so suppose that you have a signal, desired signal, you transform to the Fourier transform, you have some frequencies where the signal is strong, the desired signal is strong. So in the other frequencies, if you don't have desired signal, H in those frequencies will be 0. And in frequencies where the SNR is high, H will be closer to 1. If the SNR is low in some frequencies, H will be lower. So you can get noise reduction, total noise reduction, especially in frequencies where you don't have the desired signal or where the signal is weak compared to the noise, so you want to reduce that. So the distortion using a gain like that will come from weak or low SNR frequency components, okay? Because when we reduce, when we have a gain like this, of course we will put low gain in frequencies where the SNR is low to minimize the distortion of the desired signal. Okay, so all this makes sense. Let's continue. If you have any question, please ask, okay? Okay, so the X filter desired is simply H multiplied with F, and the residual noise is H multiplied with V in the frequency. So the variance of the signal estimate is a summation of two components. One is the variation of the filter desired, and one is the variance of the residual noise. Okay? So we want to keep the filter desired, but we want to suppress the residual noise. And it looks like this. Okay, so it's simply multiplication with the HF magnitude squared. Now let's define performance measures. Okay, so of course it's always good to define the input and output signal to noise ratio, which will give us the gain in SNR. So we define the narrowband input SNR. Narrowband, it means that we compute the performance measure for each frequency. So we have narrowband. And then we have also broadband. It means that we compute this performance measure across all the frequencies. Okay? So the narrowband input SNR, it's a function of f because we compute it for each frequency separately. And then we have the variance of x divided by the variance of the noise for each frequency. If we want to compute the broadband input SNR, so we compute the total variance of x over all frequencies in the numerator divided by the total variance of the noise over all frequencies. Okay? You see, when you compute the broadband, you don't put the integral here, but you put the integral in the numerator and the denominator, because this gives us like the energy of the signal divided by the energy of the noise. So this is the input signal to noise ratio. The output SNR, we compute it for here. Okay? So here, we can write it as X filter desired plus V residual noise. So the variance of X filter desired divided by V residual noise, we obtain the narrowband output SNR. So we see that the narrowband output SNR is the same as the narrowband input SNR. Why? Because using a gain, if we just use a gain for each frequency, scalar gain, we cannot change the narrowband SNR. So the output SNR, the narrowband output SNR is the same as the narrowband input SNR for each frequency. But still, we don't care much about the narrowband SNR. We want the output signal in the time domain to be with higher SNR, which means that we care about the broadband output SNR. So the output SNR, the broadband output SNR, we need to compute the energy of the filter desired signal over all frequency divided by the energy of the noisy residual noise at the output of the estimator. So we have this expression. So we can ask ourselves, of course, we cannot get any gain in SNR for narrowband, in the narrowband for each frequency. But the total, the broadband output SNR, can we choose H for each frequency such that the broadband output SNR will be as high as possible, for example? We will see how to do that, okay? How to choose or H for each frequency, okay? So you see that if I give you an example, suppose that I have desired signal, and the desired signal, the signal to noise ratio in each frequency is different, okay? So when I multiply each frequency by a certain number, complex number or even real number, I cannot change the SNR in that frequency. But if I keep the high SNR, so H, the gain is high when the SNR, the narrowband SNR is high, and is low H is low, the gain is low, when the input narrowband SNR is low, I will get higher broadband output SNR. Okay, because I take the integral. And you can think about it like this. Let's think about, just for simplicity, that the variance of V is constant for all frequencies. Okay, suppose that it's constant for all frequencies. Which means that the noise is white, right? It's the same variance for all frequencies. Just to think about it. So here in the denominator, we will have the integral over magnitude. So it's the norm of H. We just take the summation of magnitude squared H over all the frequencies. So suppose that we want to normalize H. This will be constant. Okay, so suppose that we would like to find H for each frequency, and we normalize it, which means that the denominator is always constant. So we can ask ourselves if we want to maximize the output SNR, we need to choose a vector H. Vector H, it's a vector because it's for all frequencies. Okay, so it's a vector from frequency 1, 2, and so on. Or if you start with frequency 0. Okay, so it's a vector that contains all the gains for all the frequencies. So we need to find a vector, and we can normalize it generally. Okay, so we don't care about the denominator because it's anyway normalized such that the norm is constant. And then we need to find this vector H such that the numerator will be maximized. How do we do that? How do we maximize this numerator when the norm of H is constant? How do we do that? Okay, this integral. Okay, so I think you know how to solve it, but even without solving it mathematically, think about if I take a vector of H, that is norm is constant. It means that if I increase one element, I need to decrease other elements. One, because the norm is constant. Okay? So for which frequencies I will choose to make it high, and which frequencies I need to make it low? Because the summation of the magnitude squared is restricted, is constant. So if I increase one value of H, I need to decrease other values. So in order that this integral will be larger, what do I need to do? It's better for me to take higher H when phi x is high, because then the integral will be higher. Which means that when the signal, this is higher, we said that this is constant, okay? Just for the example, I try to simplify things so you get intuition. So this is higher when the SNR is higher for white noise, okay? So when this is higher, we will choose H to be higher. When this is lower, we can make H lower. And then this integral will be total value higher, even that the norm of H is constant. Okay, but generally, if it's not white noise, it's very similar to what we did in the time domain. So it's based on the signal-to-noise ratio. So when the signal-to-noise ratio, we will choose high H. When the signal-to-noise ratio is low, we will choose lower H. Just like in the time domain, we took the first eigenvector of Rv minus 1 Rx. similar things, but here we don't need eigenvectors because it's just the ratio for each frequency independently. So it's even simpler. Okay? Noise reduction factor. So noise reduction factor, it means the ratio between the original noise, the variance of the noise in the input, divided by the noise at the output. So we get this ratio, which is 1 over magnitude squared of 8. If we talk about, this is the narrowband. If we talk about the broadband, so we need to take the integral here divided by the integral in the denominator. Because this is the total variance of the noise at the input, and this is the total variance of the noise at the output. Okay, make sure that you don't take integral here, because this was reduced. Okay, so you need to take the integral here. You need to keep variance of v in the numerator and denominator, then take the integral. Okay, of course, because we understand that we take, it's the energy, the total variance of the noise, the input and the output. This is the noise reduction factor. This is narrowband and broadband. Desired signal reduction factor is the ratio, this is the narrowband, desired signal reduction factor, which is the variance of x divided by the variance of filter desired. So it's similar to the noise reduction factor, the narrowband, because it's just the ratio, because we use a scalar gain. But the broadband is different, because we take the total variance of the input desired signal divided by the total variance of the desired signal at the output. So we have this ratio. And we want, just like in the time domain, we want the noise reduction factor to be as high as possible, which means that we reduce as much noise as possible. And the desired signal reduction factor, we want to have to be close to 1. If it's high, it means that we have more distortion. If it's close to 1, it means that we have less distortion. And we have this ratio similar to what we had for the time domain. You see, so these ratios are for the broadband measures. So the gain in SNR, the broadband gain in SNR is the ratio between the broadband noise reduction factor and the broadband desired signal reduction factor. Just like what we had in the time domain. You know, now after the quiz, you remember all the terms, so it's much easier to continue because you're familiar with the similar terms. Okay, let's talk about the distortion index. Okay, so the desired signal distortion index, it means how X filter desired is different than X. And we normalize it. Okay, so we take this difference, X filter desired minus X. We take the magnitude squared and expectation, and we normalize it by the variance of X. So we see that for the narrowband distortion index, it looks like that. It's 1 minus H magnitude squared. For the broadband distortion index, we need to take the integral in the numerator and the integral in the denominator before we cancel out the variance of X. So we have this expression. And of course, this distortion index is generally between 0 and 1, and we want that it will be as close as possible to 0, which means that the desired signal is undistorted. By the way, this morning we had a quiz, so people who came afterwards, they can still do the quiz after when we have a break, okay? It's just for you to practice, so it doesn't really matter. It's not like a grade that you need, but it's nice to see that you're familiar with the terms. Let's continue. Mean squared error, which is a very important performance measure. By the way, we like mean squared error many times. Why? Because it's usually it correlates with the performance of many applications. Because if the mean squared error is low, it means that the performance is better. But generally, it's not always